let's tackle a few examples on pressure. So here's the first one. So if a tire has a gauge pressure of 30 psi, then what is the actual absolute pressure in the tire? Okay, so if you're given that the gauge pressure in this case, so I'll just designate it as P, and we can actually write gauge in here. So if this is 30 psi, now notice we can change the psi, so I can do the conversion there. So 1 psi, this would be 6895 pascals. Okay, so the psi's would cancel. And let me take out the calculator here. So we're going to get 30 multiplied by 6895. So we have quite a bit of pressure, which is the gauge pressure in the tire. Now, in this question, what it hopefully is nudging you towards is the fact of understanding a difference between the gauge pressure, kind of absolute pressure that you have, and also the atmospheric pressure. So in general, what we have is that the absolute pressure, so absolute pressure is equal to the atmospheric pressure, so whatever we have the pressure in the atmosphere, which is outside of the tire, and it will be the pressure plus the gauge pressure, okay, that we have, which we just found right above. So we can substitute this back in here, okay, and we know that 1 atmospheric, okay, is equal to, so in this case 101, they give that to us. So we can add up these two together, and that's going to be the pressure, which is the overall pressure in the tire. And it has to be bigger than the atmosphere, otherwise the tire would just simply be flat. If you don't pump up enough, and if you don't change the pressure inside the tire enough, it's just going to be a flat one. And if it's above, okay, then it's going to start to inflate, okay, and it's going to get, more firm as you're going along. So this indeed would have been the pressure, okay, that we have. So I'm going to just add these two together. 101, this is 325 equals, so this is 308,175 pascals. And you can round it to whatever it is that you like in here. So if you round it to, let's say, 3 sig figs, it would have been 308,000 pascals, okay? Or you can round to one significant figure or whatever it is that you like. But that is all that you would have in here. So it's just a matter of understanding the equation for the absolute pressure, that you have to add up the atmospheric pressure to it. All right, so that's the first example for you. Here we have the second example. So we have a figure below, and we want to calculate two items in here. So notice part A and part B. So basically, this is kind of utilizing Pascal's principle. Okay, so if you have a container and it's filled up with fluid and it's fully enclosed, then we know that the pressure will be transmitted, okay, undiminished throughout an actual fluid. And this is just Pascal's principle, okay, that we have in here. And in particular, okay, if as you can see there, these things are exactly at the same height, okay, so as you're going along, so that means that whatever pressure that you have in here, so this is pressure P1, is going to be equal to the pressure P2 all the way over there. If the heights are different, then, the pressure gets passed along, but of course there's also then the actual height that you have to worry about. But in this case, we don't have that worry because they're at exactly the same height. All right, so how would we tackle this? So as I said, so here, let's just kind of designate this as pressure P1 and then pressure P2. So this is for part A. Now, since we have the figure, I don't have to really draw anything. So we know that pressure P1 is going to be equal to the pressure P2. So whatever we have in there, okay, so that pressure gets passed along, and this is the gauge pressure that we would have. Now, pressure is nothing else but the force, okay, divided by the area. Now, can be force F1, and then area A1 is equal to force F2 all over area A2. Now, why do I put that in there? Because they give us the force, okay, which is the first force, which is 85 newtons. They give us the radius, okay, so within here, so notice that we're going to be using pi r squared for the circle in terms of the area that we have. And we're supposed to find F2. Okay, so if we plug all of this in here, so this is going to be 85 newtons. It's already in metric standard units, so this is going to be pi. Now my r for the first one is 15 centimeters. okay, so this is what I have in there, so it's going to be 15 centimeters squared, is equal to the F2, okay, so within there's what we're trying to find. So I don't know what that is exactly, but I do know, okay, that this is pi, and then this is, I guess, 60 squared. All right, so we have that. Now you might wonder, oh, you didn't put metric standard units in here in terms of the actual radius. So the reason for that is because I have, if I have centimeters squared over here and I have centimeters squared over here, they're going to cancel out anyways. Okay, so because if I'm going to be solving this out, so notice what happens is that F2, okay, is going to be equal to just 85, and then multiply both sides by that area, so pi, okay, of 60 squared, okay, divided by, and this is pi of 15 squared, so the pi's cancel, and notice that you have centimeters squared on top and centimeters squared at the bottom. So you can certainly change this to meters. The ratio is still going to be the same. And that would have been our answer for F2. Okay, so let's take out our calculator in here and let's see what we get. So we have, this is going to be 85 multiplied by, this is 60 squared, and then divided by, this is going to be 15 squared. So my force, okay, so as I'm going along here, is 1360 newtons. Notice that I did keep the 85 in newtons, so this is still going to be newtons. Now they don't really tell us again with the round, so if I take a look at this, you can round to whatever you like. One significant figure, I guess that's the maximum in here. Okay, so if we did do that, okay, if it was the 1 sig fig, it would have been just 1000 newtons. Okay, so within there, but you can round to whatever it is that you like. I'm actually going to leave it like this. Okay, so you can check your answers as well. All right, so that would have been part A. Let's take a look and dive in to see what we would have to do for part B. So for part B, now we're finding the first force, but they give us all of the rest. Okay, so in that instance, okay, so I'm going to just copy this just so that I kind of don't have to flip back and forth. So let me copy that and bring it down here so that we have it and make it very visual for ourselves. So this is B. So this is the same thing. So we're gonna, if we go back into this figure, okay, so this kind of the pistons, okay, that we have in here, so we're kind of pushing, we want to know what that force F1 is for this. So it's going to be exactly the same formula. So that means, your pressures, okay, are equivalent. So this whole thing, going to duplicate it, we can bring it back down, and we can fill it in with the given information. So in this case, we're going to have F1, which we're trying to solve for. This is going to be pi. My radius of 1 is 5 squared, so the same thing. I'm going to just keep it in centimeters because I have the other one as well. And then this is going to be 320 newtons all over, pi, and this is now 60 squared. The pi's will cancel, okay, each other out, and we're going to have F1 is equal to 320 multiplied by 5 squared divided by the 60 squared at the bottom. All right, so let's take a look and see what that would be. So if I plug this back in here, so 320 multiplied by 5 squared and then divided by 60 squared equals, okay, and notice that it's a very tiny force, so 2.2, etc. And again, okay, if it's only to 1 sig fig, it's just 2 newtons of force. And that is very tiny, right? So notice, what happens in here, okay, you have 320 newtons, okay, on the opposite side, but here only 2 newtons, okay, on this one. So it's quite a huge contrast when the pressure just passes along. So this is certainly done, okay, because of the fact that the radiuses do change, all right? So that is it, okay? So for this example, there isn't really anything else to do here, but this is a great example of utilizing Pascal's principle and knowing that the pressures, okay, are the same at the same depth, all right? That's it for this one. Here's the next example. So here's a very interesting one. So we have a dentist, and that dentist can easily move a patient upward by simply pumping a small foot pump that is attached via a tube to the chair. And this indeed, okay, is true. You sometimes would have that. I mean, now it's pretty much electrically done, okay, but you can certainly pump up this thing, and it's pretty neat because it's kind of the utilization of Pascal's principle, okay, for static fluids. So let's see, okay, what all of this is. So the patient on the chair has a mass of 75 kilograms, and then the chair has a mass of 150 kilograms, and is pivoted on a circular plate with a radius, okay, of 65 centimeters. So we kind of have something like this. So let's this particular kind of plate, okay, maybe it's something like that, and then this kind of funnels in right into, okay, a little tube, okay, and it gets passed along in here, and maybe this is the little pedal, right? So where the foot kind of presses down, okay, this is the leg, and the person, okay, sitting on the chair, okay, etc., okay, is right here. So the mass of this entire thing is pretty big. It's 75 plus 150, so it's 225 kilograms. So as you know, this would have been very difficult to try to lift someone, okay, and a chair that's that heavy. I mean, I certainly wouldn't be able to do it. But yet, we can, pump, okay, our foot a little bit, and, the chair is going to start to slowly go up with the patient. So, what's happening in here? Well, what's happening in here is that you have a fluid, okay, which is kind of filled up, okay, and we know that the pressure gets passed along from one side to the other. Okay, so I'm going to say that, okay, so this is pressure P1, okay, and then, we have pressure P2, okay, which is passed along as we're going through. So we have the mass, and if we have the mass, that means we know what the entire weight, right, is. So the force of gravity, okay, or the weight of the patient, okay, with the chair is mass times gravity, which is 225 multiplied by 9.8. So that's the actual weight or the force, okay, that we have to kind of overcome. So this is 225 times 9.8, and you'll see that it's rather pretty big. So, okay, it's about that much. And this is in newtons. So now, once we have this, okay, don't forget that pressure P2 is the force, right, which is over the surface area. So this is the force, okay, that we would have to apply to lift this person up, okay? That's the minimum amount of force that we would need. So we have that particular force. Now, what else do we have in here? So they say that this thing is pivoted, okay, on, so this is the radius of 65 centimeters, okay, so within here. And then the small little pump, okay, so this right here has a tiny radius, okay, so it's just 0.25 centimeters, okay, so very tiny in comparison to the other one that we have. And then it says, then what force, right? So we want to be able to figure out what the force is here, right here, right? So what's the force, I guess, F1, that we need to utilize, okay, or the dentist needs to utilize, okay, to lift this patient up. All right, so let's try it. So we know that pressure P1 is equal to pressure P2. This is by Pascal's principle. So now we have what the force, okay, so this is F2 over the area, okay, this is on the side of the chair. And then now the force F1, okay, over the area A1, okay, we have to try to see if we have that. Well, we've just found the force, it's 2,205 newtons, divided by, this is pi, okay, now the radius is 65 centimeters squared. All right, so this is what we have over here. Now you can change that to metric standards. I'm not changing it because of the fact, again, that I'm going to utilize just centimeters on the other side. Just make sure that the unit is consistent. So this is going to be pi. And now this radius is very tiny, okay, so squared. And now I can find out what this F1 is. All right, so this is going to be 2,205 multiplied by pi times 0.25 squared. So I'm taking this, again, multiplying both sides by it, so it gets shifted on the other side, and then divided by what I have over here. The pi's, of course, cancel, and I can substitute this into the calculator. So let's see what we're going to get here, and you'll be shocked, how big of a difference that is. Okay, so there you go. So if you substitute this whole thing in, you're getting 0.03, 26, etc. newtons. All right. So if we wanted, I think we had what, 2. Okay, so let's just keep it to 2 significant figures. But it doesn't matter. Okay, so if you, whatever you want to keep it to. The point is, look how tiny this force is. Now you're not technically are going to get, this particular radius as big. It's not necessary to make it that big, okay? But the idea is to make you think that, oh, I can use these static fluid, okay, things that I learn in pressure, where that pressure just gets passed along. So because of that pressure, it gets passed along in enclosed fluids, it utilizes, okay, quite a bit. And we can just take our foot and just slowly tap and then start the patient to lift up. So if you've ever wondered why, well, it's because of Pascal's principle, and we're using it wisely because we're making the radius bigger, okay, on the other side, where the fluid kind of pushes up, and then we're making the radius much smaller where we're pushing. Now, there is, kind of a trade-off in here because of the fact that you're going to have to push quite a lot of times, okay, to lift the patient up, right? Because this is just work, right? So the law of conservation of work, it's not like you're going to get magically. So, this patient gets moved up, but, it's at an expense. Like, you're going to have to tap this thing a lot of times, to get it to a certain height. Because remember, work is force times the displacement. So in this case, it's the potential energy that we're giving, okay, vertically to the patient, okay, on the chair. So that actual height, okay, or the displacement itself, well, you're gonna have to keep pumping quite a lot to match the same amount, okay, as you're pushing through, okay, that patient. So that's the trade-off. But this is a great example that tests your understanding of Pascal's principle. All right, so that is it, okay, for this one. So there you have, okay, the tiny force. Here's the last example of this video. So there's 2 components in here, and it's an awesome example. It's to do with a manometer. So a manometer is basically a device that looks like this. It's kind of a tube, okay, that we have. It's kind of, cylindrical tube that kind of goes in this particular shape that you see in here. And it is capable of measuring kind of gauge pressures depending on the height of the fluid inside and whatever you might have. The blood pressure readings originally kind of were done exactly in this fashion. And I can put up a link up above there if you're interested in trying to figure out how that blood pressure gauges readings actually worked. All right. So for this example, let's see what they have. They say, for part A, so this is figure number 1, okay, so this is this figure. So notice there is a change. In this figure, the height, okay, of the fluid goes up in this way. In the other side, okay, the height of the fluid goes up on the other side, right? So this one is actually going to be negative gauge pressure, and this one's going to be positive gauge pressure. All right, so this is what we will have. Let's try to find out why it's negative and why it is the other one positive. So assume the fluid inside the manometer has a density. So they give us a particular density, right? So within here. The height rises, okay? So notice that the H rises 23 centimeters, okay, in here. You know what? I'm going to just write it in. 23 centimeters in there. And then here's my density, which is 7.6 times 10 to the 3. It's kilograms per meter cubed. So it's already in metric standard units. So let's change this to metric standard units. The atmospheric pressure is just 1 atmosphere. All right, so this is just 1 ATM, okay, and that 1 ATM, so notice I do give you, okay, what this is in here, but you can obviously look it up, okay, if you're doing this question on your own. So that's what we have. Those are all the given pieces of information. This is for the first figure, so this is part A. Now, they ask us to find what the pressure is, okay, so what this pressure is, and then they ask us to mention what the gauge pressure would be, like what would the actual reading be and what does your gauge pressure reading tell us. All right, well, I've kind of spoiled it because I said that, that it's going to be negative, right? So we have a negative pressure, okay, in here, and so we'll talk about that in just a moment, and this is why the fluid actually rises, okay? So let's do all of these calculations. So this is now your understanding of pressure within fluids. All right, so pressure is always the same at the same depth. So if you kind of go all the way here, notice that the depth over here and over here is the same. And this what this tells us. Okay, this is kind of like through Pascal's principle, okay, that we can obtain, and also just pressure at depth of fluids. So we have the following. So the pressure, this is on the figure number 1. So the pressure of the atmosphere, if the two pressures are identical, so meaning this pressure P1 and then pressure P2, if these two are the same, then P1 is just the atmospheric pressure, which is kind of pushing down there. And then pressure P2 is going to be the pressure that is kind of inside over here. So, right, so that pressure plus whatever pressure we have from the actual fluid. Now, that pressure is going to be density times gravity times the depth, okay, or the height. And this is just coming from understanding pressure at a depth, okay, of a fluid. So if you want to find this out, well, they give us the atmospheric one, which is 101, let's say 325. I want to find out what this is, but I do know, okay, that the density, so this is going to be 7.6 times 10 to the 3 times 9.8 and then times 0.23. So let's see, what all of this junk is in here. So it's going to be 7, I guess I'll put it already. Okay, I'm going to get rid of the scientific notation, times 9.8 and then times 0.23. So we have all of this pressure, okay, right there. This is just from the fluid. Now we're going to bring this over on the other side, right? So because we want to isolate for PA, okay, so for this pressure, so that's going to be the atmospheric pressure, which is all of this, minus, right, minus all of this. All right, so let's punch that in there. 101, 325 minus 17, 130.4. So this now becomes 84194.6, and this is going to be pascals. All right, so just be careful, okay, because this is PA and this is PA. This actually means the pressure A, so pressure applied. Okay, so this is what it would be. Notice that it is below the atmospheric pressure, right? So it is actually below it. And so what that means is if you're below it, then your gauge pressure is going to be negative. Now, don't forget, what is gauge pressure? So when you're talking about gauge pressure, so that is your absolute pressure, okay, that you have is always equal to, and this would be the atmospheric pressure, okay, that you have, plus the gauge pressure, so the P, and the gauge pressure. But hold on a second, what did we just do? So if I go back to this, okay, original equation, so here over here, if I bring this over, okay, on the other side over here, what I'm going to get is I'm going to get P atmospheric, right, plus, now I'm going to bring in the negative because it's going to be negative, okay, the density, so let me just, so it doesn't look exactly like a P, so density, okay, of GH, right, so this is P atmospheric, right, so P atmospheric plus whatever your gauge pressure is equal to the absolute pressure. Well, so this is your atmospheric pressure plus, okay, whatever this might be, okay, and this means that this is the gauge pressure that you have. That's your gauge pressure within there. And notice, okay, so because the plus is in there because I brought in the negative, that's going to be negative right there. So if I wanted, to take this whole thing in here, so my gauge pressure is going to be negative 17130.4 pascals. So of course, you can round this to as many significant figures as you like. I'm going to leave it as is for the moment, right? So your gauge pressure is negative. The meaning just means that you're under negative pressure, right? So this just means you are below atmospheric pressure. So when you get a negative reading for your gauge pressure, it doesn't mean that pressure is negative. It just means it's below atmospheric pressure. And we call that negative pressure, right? Okay, so that's why the atmospheric pressure, as you can see there, it's pushing and the liquid is kind of going up because of the fact that the pressure, that PA that we have in there, which basically would have meant the absolute pressure within, would have been, okay, below that atmospheric pressure. And that's why that fluid is going to go upwards, because you're going to have that extra gauge pressure coming in. All right, so that is it. Okay, so here is your atmospheric, here is your gauge pressure. If you wanted to round, so let's say it looks like everything is 2 sig figs, so you can do that, which would have been around 84,000 pascals, okay, for PA, and then about 17,000, which is negative, for the gauge pressure. All right, now what about figure 2? So what about this, the second figure in there? So let me put that in here. I'm going to just add in a page for myself. So if we have now all of this, I'm going to copy this down, okay, within here. Let's copy this. Hopefully I can bring it down in here. Okay, well, this is not what I wanted, but I can shift this around so that it kind of just removes this out of the way, and then I'm going to get all my things that I need. All right, so if you were trying to do this, now all of a sudden, notice that, okay, what is happening is the two pressures, so it's going to be P atmospheric is going to be equal to, and my apologies in there, so it's going to be P atmospheric plus, okay, the height of the fluid, which is going to be density times gravity times the height of the fluid, okay, within there. It's going to be equal to the PA on the opposite side in there, right? Because this is now pushing in. So that means this must be higher than the atmosphere, right? So this must be higher than the atmospheric because it's pushing up the liquid, right, as it's going through. So in order for them to balance, it will keep pushing this up until eventually the atmospheric pressure plus the pressure coming from this fluid is equivalent, okay, to this pressure pushing it down, right? So they're going to be basically at an equilibrium at some point. Now you can punch in all the numbers. So this is 101, 325, 101, 325. However, now we have, we've kind of calculated. Let me just double check. Okay, no, they changed this. Okay, so they changed the density. Now it looks like it's density of water. Okay, and then they changed the actual height, which is 45 centimeters. Okay, so let's do that. So this is water, so 1,000, so times 9.8, and then times the height, which is 45 centimeters, and that's going to be equal to, okay, so all of that is to that PA right there. All right, so let me shift this out of the way. Okay, so it's going to be something like this is equal to the pressure, okay, on that other side. And this would have been your gauge pressure. Now notice the gauge pressure is positive, right? So if you're reading out the pressure, so out of here, this is what we would read on the gauge meter. So all of this, it would just tell us that that pressure is above the atmospheric pressure by that amount. So now let's see what that would be. So it's 9.8 times 1,000 and then multiplied by 0.45. So what we have, this is 101. So let's punch this all in. 101, 325 plus 4410, and that's PA. So answer plus 101, 325. So that's 105,735 pascals. All right. Okay, that's what we would have had. That's for PA. And then your gauge pressure would have been this. So again, rounding to 2 sig figs, you can round that up to be about 100, I guess 10, okay, rounded, 1,000 pascals, and then the gauge pressure would have been just 4,400 pascals. So that's what you would have had, okay, for these. And that is pretty much it. This is a great exercise, forces you to understand gauge pressures and also, okay, kind of the absolute pressures, okay, within, and how to use the manometer. Okay, thank you for watching. We'll hopefully see you in a future video. Bye, everybody.